Hey everyone, let's talk about the cross product now. We've looked at what it means as far as conceptually when I show you the strings, but now let's do an actual vector cross product, or the cross product of two vectors. So keep in mind, W was one vector, so I give it an X, Y, and a Z component in the I, J, and K direction. Okay, we're going to work strictly with Cartesian format here. The red one, R, has an X, Y, and Z component in I, J, and K directions, okay? One thing I'll point out real briefly here, I don't use this very often, but the magnitude of the cross product, W cross, notice the cross here, R, the magnitude of W cross R is the magnitude of W, the magnitude of R, right, the size, times the sine of theta. So notice magnitude, magnitude, sine, there's no IJs and Ks over here because it's all sizes, right? So this is the size of the cross product. But let's find the cross product of the two vectors. Remember that was purple in color when I used the strings. So the purple vector is the cross product of W times R, WXR, W cross R, not WX, W cross R. And we do this by use of a determinant. So if you haven't used determinants, I'll show you what we get here in just a minute. I should point out that W cross R is exactly the opposite, negative-wise, as R cross W. So a vector cross product is not commutative. The dot product is, but the cross product is not. It is not commutative. And when I'm done, I get another vector, right? So if I'm going to have a string of cross products, I got to be really careful about which pair I do first. So it's also not associative. That is to say, real briefly, A cross B cross C, put the parentheses there, that's not necessarily equal to A cross B cross C. All right, so we've got to be really careful with that, okay? So they're not the same thing. All right, so let me get rid of that. All right, so if I do this, I'm going to have a J or an I component, so I'm going to get I hat here, and then I use the minor, so I take out the row and the column that the I is in, so the first row and the first column, and I'm left just with this right here. So I get WY, WZ, R sub Y, R sub Z. Okay, so notice that this is going to be the X component of the vector P, but it's created by only the Y and Z components of W and R. Kind of interesting to note. So the X component is not affected by the X components of the two vectors that created it. Then I go to J and I put a minus sign because that's the way determinants work. I apologize if you haven't seen determinants. And then I put in, take out the row and the column. I'm going to get WX, WZ, and R sub X, R sub Z as another smaller determinant. And then finally, plus K hat. And then I'm going to take out this row and this column, and I just get these four right here. So WX, WY, and then R sub X and R sub Y. Okay? And when I put all of that together, I'm going to get WY, put an equal sign here, WYRZ minus, you know how to work determinants, you know what I'm doing here. If not, just kind of write down this result. WZ R sub Y, okay, that's going to be the X component. And then I'm going to get the minus sign out of there. And I'm going to do WZ R sub X minus WX R sub Z. All right, it should be this way, then this way, but I got this minus sign, so I do it backward. That's the J component. Finally, WX R sub Y minus WY R sub X. And that's the K hat component. And so you can see that I've created another vector with this vector cross product. So if you just write this down, it doesn't matter if it's A cross B, just make the W's A's and the R's B's or whatever, it doesn't really matter. But you get the idea. And again, this creates another vector. This is the third vector, P. And this vector is perpendicular to W and it's perpendicular to R. And I call that mutually perpendicular to both of those. And if you get zeros across the board, it's because these two vectors are along the same line, or they're either parallel or anti-parallel. And that'll give you 0. Okay? If you have any questions, be sure to leave them in the comments below. Thank you.